All right, this is the fifth and final problem from quiz number 2. Here we're trying to use the second fundamental theorem of calculus to compute integrals. So this first integral, we're trying to compute an integral for cosine. So just quickly, let's draw it since we can. We're trying to go from 0 to pi over 4. Now, let's say I know at pi over 2, the value of cosine is 0. And at 0, the value of cosine is 1. Pi over 4, that's somewhere in the middle. And let's see, what was that? Cosine of pi over 4? Yeah, it's like root 2 over 2. All right, so root 2 is about 1.414, so cut that in half, about 0.7. So, okay, so maybe about there. So root 2 over 2. Cool. All right, so we would come down and we'll hit it about there. So what we're looking for is this area in between 0 and pi over 4. Now that's not necessary for us to graph this in order to solve it. However, if you can graph something pretty easily, you should do it, if only to give you some idea of what the solution, should look like. For instance, we can see immediately this should be a positive number, right? It's all above the x-axis or t-axis. Okay, fine. We also could do a quick estimate, right? We could say, well, if I just did a rectangle here, it has height 1 and base pi over 4, so the area should be a little less than 1 times pi over 4. All right, that gives us a reasonable ballpark. Okay, but how do we actually compute it for real? Well, we want to use the fundamental theorem of calculus, the second part. So I'm going to use FTOC2. And that says first thing you need to do is find an antiderivative for this, right? We view this as a derivative. And I want to find the original function because, again, FTOC2, right? FTOC2 says if you want to integrate from a to b and you have the derivative of a function, then this just becomes the antiderivative or an antiderivative evaluated at at b and at a. Right? Or remember, we might write this as f between a and b. Okay, so in this case, we need to find a function whose derivative is cosine, and we know that that's sine. And then we want to evaluate sine between 0 and pi over 4. Okay, well, let's see. At pi over 4 and at 0, we actually know the values for sine. So sine of pi over 4 is root 2 over 2. And, well, sine of 0 is just 0. So actually our exact answer should be root 2 over 2. Okay, what about this second problem? Well, the second problem, of course, we want to apply the same technique. We want to view this as the derivative of something. And already that makes us a little bit nervous because this is a complicated function. Okay, what can we do? Well, I see a function, t squared plus 1, and its derivative, 2t. So I think we should use substitution. So we try a little substitution action. U is equal to t squared plus 1. du is equal to 2t dt. And if I do that, then, well, I still have t equals 1 to 4 here, but I can now replace e to the t squared plus 1 with e to the u. And then 2d dt just becomes du. All right. So from here, there's two ways you can go. One way involves changing your t's in the bounds to u's. The other involves back substituting at the end. Let me show you both approaches. So one approach, I'm just going to find an antiderivative. And an antiderivative for e to the u is e to the u. And then I need to evaluate between 1 and 4. Well, those are t's and those are u's, so let me put the t's back in. So I get e to the t squared plus 1 between 1 and 4. And so this will be e to the, let's see, 4 squared plus 1 is 17, minus 1 squared plus 1 is 2, so e squared. Okay, so that's one approach. The other approach is I'm going to replace my bounds with u bounds. So let's do this over here. If u, or rather if t is equal to 1, then what does u equal? Well, when t is equal to 1, I get 1 squared plus 1 is 2. And when t is equal to 4, the upper bound, I get u equals 17. And so I can go from 2 to 17, e to the u du, which will be, again, we know an antiderivative is e to the u, but now u goes from 2 to 17. And so I get e to the 17 minus e squared. Okay, same answer either way.